So this is a big topic. I'll try to do some justice to this. In general, autonomous vehicle is a complex topic, and perception and planning are at the core of autonomous vehicle. So we're trying to address a part of the equation here, which is the planning today. And before we dive into that, we should try to understand what are we talking about when we say autonomous vehicles. I'll try to go with that introduction first, and then I'll once I bring what is autonomous vehicle and a different level of autonomy, then I'll try to show some current trends and benchmark some leading OEMs and startups, what they're doing, the survey of that, and then we'll dive a little bit more to different layers, basically the architecture of planning and controls, and look at piece by piece, different pieces of that, and maybe do some survey of what are the state of the art algorithms that are being used to best or worst, but many different algorithms, and we'll try to survey them. I'll also, interestingly, I'm going to kind of showcase very cutting edge technology, not going into technical details, but more like an overview. It's reinforcement learning. It's kind of starting to get a lot of traction these days, mostly for higher level of autonomy vehicles, and it has a critical role in planning. So I'll just show some examples of that. Then we can also go through some typical job roles that you can expect when you go into this domain, and also how to basically get started into this domain if you are not in this domain already. So with that, let's first start about introduction of what is autonomous vehicle and different level of autonomy. According to SAE, there are, depending on, actually there are some couple of different opinions, but usually I have seen 0 to 5, and sometimes some people have shown level 6 also, but mostly it's level 0 to level 5 of autonomy. Like you can see in the screen, the blue ones are more like 0 to 2 level of autonomy, where it's more the driver has to be kind of in charge of the whole system, whereas level 3 to 5 are where it's more towards full autonomy, level 5 being fully autonomous vehicle, and level 3 being kind of in the border. 3 to 5 is where driver doesn't really have to be either engaged that much, or for level 5 even be present, like it can be a totally driverless vehicle. So we should go some look at some examples, but also keep in mind, like the depends on where are you operating. That is also very critical. Some except level 5, which is supposed to be full autonomy everywhere, and the definitions can be applied subjectively. If you are working on highway versus urban road network versus parking lot, there are different applications, and something that is level 4 certified in highway might not be level 4 certified in urban roads, basically. So let's look at some example features. Level 0 features are mostly present in today's vehicles. They are your blind spot warning, automatic emergency braking, some lane departure warning. At least the luxury vehicles, all of them, the premium vehicles, all of them have these kind of features. These are not a very non-invasive type of autonomy and lane departure. Mostly they are warnings, and sometimes they have little nudges and all. The level 1 are also a lot of these features people already experience today. Adaptive cruise control or lane centering. Usually when we say level 1, it's only one of those features are present. Level 2 is when you have both of the lateral and longitudinal control, like steering and your axle brake pedal control. That's your level 2 system. So level 2 basically means that you are getting that autonomy, but driver is still responsible for everything. So usually his hands should be on steering wheel. A lot of time there would be driver facing monitoring cameras, which are steering wheel touch sensors, which will try to make sure the driver is engaged. It gets a little bit more tricky. Level 3 is where driver is not supposed to be engaged, except when the system determines that there is something that it cannot handle on its own. It should understand that and go and tell the driver to take over and give the driver some wiggle room, some time to take over, like 5 to 10 seconds, and then the driver takes over, and then he can give control back to the system when the system is ready again. And level 4 is where none of this should happen. If there is such situation, for example, if there is a highway, some kind of problem happening, then it should go and go to the roadside and the car on its own and call for help and all those things. So that's level 4. And level 5 is basically level 4 everywhere on all weather conditions and all road conditions. Like, now that that is clear, we can see what are the current market offerings for some of these features. As you can see, most of these are premium or luxury vehicles: Tesla, Cadillac, Mercedes-Benz, BMW. Level 0 features are present probably in more than luxury and premiums today. Level 1 features like lane centering assist, emergency braking assist, level 1 parking assist, where only steering is controlled by the park assist and the driver actually is controlling the axle brake, those kind of features. Then you have level 2, which I said, like, where kind of our true autonomy is really coming into picture gradually. It's highway assist or lane change assist, traffic jam assist, some stuff like that. Tesla Summon is considered level 2 feature as well. Level 2 parking assist is also basically where you have lateral and longitudinal control simultaneously of your park assist. Level 3 is this is where kind of you can see the slide I have mostly showing OEMs here. So the OEMs are giving your regular these kind of features, level 0 to 3 features in your consumer cars. Beyond that is a little bit tricky, because when you go to level 4 and level 5, some manufacturers are claiming they're going towards that level 4 and level 5 requires a lot of redundancy in hardware, software, and it kind of becomes cost prohibitive to give that to a consumer, except maybe ultra premium. But for all that matters, a lot of what we are going to discuss today is basically common between level 2 to level 4 or 5 for that matter. From planning perspective, we're not going to discuss safety and redundancy and all those things, which are basically where you get level 4 and level 5 architecture differs considerably. But having said that, level 4 and level 5 are actually this slide I'm presenting. That's where the robotaxis come in. Robotaxis can now, these are mostly not directly OEMs working on this, but they're probably working on with partnership with the startups. I have mentioned it's a little bit smaller, I think, slide, but Waymo, Lyft with Aptiv, and then the Aptiv had a new collaboration with Hyundai called Motional, Cruise Automotive working with GM, Baidu, Pony.ai, WeRide. These are really there are a lot of names, and these are some of the leading names here. The difference here is that these cars are really more costly than your consumer cars, by a scale of probably 5 times to more. There are a lot of sensors, a lot of redundancies. There are probably two different set of sensors. If first set of sensor fails, two different kind of algorithms. Everything is there, and also these are meant. This kind of algorithm, this kind of taxi set. When you are using this, you can perhaps control in which operating area you will use. These are perhaps targeted to like ride share basically applications basically. Another thing is like these are supposed to run 24/7, so they can recoup some of the cost that would be, like the use case is much better here. Having said that, like I said, like it doesn't really matter that much for motion planning and controls, because at least for the code algorithms for that, because usually redundancy is built around that in the architecture. The only difference is like level 4 and 5 is where maybe the driver is not so much present, or the driver interventions are less. Actually, level 3 is where you kind of get all the complexity of handling with the driver, basically level 2 and 3. Having said that, this is just one presentation of what could be a AV software architecture, but not necessarily. I mean, everywhere you'll probably find a little bit difference. On the left hand side, you have, of course, the sensors, and mostly these are smart sensors. These sensors either give like images, or for the lidars it point clouds. For radar, object detection, or radar points also. And then there you have a sensor perception algorithm stack, which can kind of abstract that algorithm, or like I said, a lot of times what we get is basically smart sensors which have those software inbuilt, and then they give object information to the next layer, and road information, position, vehicle states, and all those things. And with that, that's where you have usually two different set of sensor fusion algorithms. One is for the object detection, object sensor fusion, and one is the localization sensor fusion, basically a post vehicle or ego vehicle. With that information, you kind of try to build a world model of what is going around you, along with map information that is coming from the database, and like you get a bird's eye view of this is where the planning kind of starts. And I have tried to encircle with this shaded area. So you can see these four layers of the planning. One is world model, one is behavior planning generation, one is more traditional motion planning, and then you comes the vehicle control. So world model is where you are abstracting. Now I'll go into a little bit more details in the next few slides, but world model is where you are trying to get all these sensor information, sensor object information and map information, and combining them together to one blob of data that is more like a scene. Pretty similar to what when you drive as a driver, what you do is like you do not look at your eyes, which are also camera, like which is giving object images, sensor to your brain. You just look at object level information and have some abstraction of how you deal with a scene. Basically, this is kind of try to. So the next level would be behavior generation. High level, what it does is basically for level 2 and 3, it will do some interaction with driver, but more importantly, what it will do is basically take high level planning actions, like lane change, lane keep, and a lot of constraints. Basically, it will try to kind of be the high level brain of the planning stack. It tries to look at the rules of the road, traffic light, traffic sign, and all those things, and give a more easily solvable problem to the next layer, which is path and motion planning. The motion planner actually basically takes this in kind of constrained domain in which it needs to work, like either it's a lane keep when it is one lane, or if it is lane change, it needs to look at two lanes. And then it also have constrained information like a stop sign or stop light from behavior planning. And then it tries to generate a trajectory, basically, that it wants the driver, or sorry, in this case, the controller to take. So that trajectory information, which is a sequence of points basically in space and time, with velocity and location of those points. And then objective of the controller is to basically follow those sequence of points, and these are done dynamically at every time step. So, and then the controller basically trying to take that, and then that is like a reference to it, and it tries to come up with control efforts in terms of axle and steer, axle, brake, and steer commands basically, and then that goes to the actuator interface. So, having said that, this is just a little bit of pictorial depiction of what I just mentioned. The one critical thing is the environment modeling, which I was saying is basically the input information comes to the motion planning and control stack from here. Think about this as like we are basically almost like doing automated driving is like playing a game, right? So you're getting a bunch of information like objects and space and map information from the sensors and the map and some processed sensors basically, and then you have some kind of a data structure with which you will represent your problem to the depending on which every scenario would be different depending on whether you're on highway or urban network or near a intersection and all those things, and you basically have different think about that as a like different part of the game basically. So that's how the usually the problem is solved, and you have a then comes a hierarchy of plannings like I mentioned. There is first a route level planning which takes this user which basically you can think about like navigation route also, or maybe more detailed route. Navigation route is usually road specific. Here you probably solve a lane specific problem. You get the planning problem is then planning and control problem takes all this information from the environment model. One more important thing I forgot to mention, this is kind of in the in-between domain between planning and perception called prediction. Prediction is basically where you try to get the trajectory, threat assessment, and collision detection, collision projection for the other actors. You need to look at their trajectory also, and that is basically using the perception information and the rules and all the other. So you're basically almost like doing a low fidelity planning for the other objects, a trajectory plan basically for them, not to the same extent that you will do for the host vehicle, but on a more rough basis. And then, so coming back to the planning domain, you get this route plans where it will tell you sequence of roads or lanes you have to take. Then a behavior layer, which will take, depending on those lanes you have to take, it will tell you and also depending on the traffic that is present, it will tell you to do lane keep, lane change, and how to do the lane keep, and where to do the lane change, and all those things, and where to do stop and traffic assist and all those things. And then the motion planning is now you're getting a little more finer. Now you're getting sequence of points that you have to follow for the host vehicle. And then you have feedback control that tries to follow that sequence of points by applying, model-based feedback control, and comes up with steering and axle and brake torque. Again, like this is, I'm repeating this because this is probably the main part of the discussion here. So you have environment modeling, environment modeling, which is basically completing fully or partially observable perception knowledge and combining the perception knowledge with map and environment knowledge to represent a semantic and some kind of a data structure basically for the planning to work on. I've mentioned the input output, kind of what I mentioned before. It gets information from perception and map everything, and output is a modified scene basically. The route planning is doing some graph search basically, and then it's giving you an optimal sequence of roads and lane segments to take. The vehicle model library is basically a modeling library because you have different level of fidelity of, some you have kinematic and dynamic bicycle model, or, even high level non-linear bicycle vehicle models, and, or something for like behavior planning might even use, or motion prediction might use point mass acceleration, point mass model. So all these things. Then object prediction is the prediction of the other actors' trajectories, environment modeling, and then go between these slides. Behavior planning is like high-level decisions, basically, whether you want to do lane keep and lane change, and kind of their, um, you know, between what distance you have to do that and all those things. Some high-level information to motion planner. Motion planner then gives you a sequence of waypoints to follow. Let's say like a 1 meter space for next 7 seconds. What you have to do, something like that. The motion control is then just one value of steering angle and acceleration and excellent brake torques, basically. Now I'll go to a little more technical here. What kind of algorithms are usually used here? Environment modeling is your typical coding, object-oriented programming, and Kalman filters, route and mission planning, a whole bunch of algorithms. This is your Google Map and Waze, basically. A lot of A-star variants, dynamic route planning, D-star, vehicle model library, like I mentioned, kinematic dynamic bicycle models and more nonlinear models. Object prediction use Kalman filter, HMMs, neural net, and all those things. These are more into perception, though. Behavior planning are heuristic methods, cost-based online simulation. For more state of the art, it's reinforcement learning, which I'll briefly describe, like I mentioned before. Motion planning actually usually is separated into two parts. One is one is path planning, where you get the XY path, basically, and then you have velocity planning of what speed you will have in all those path points. So lattice planner, polynomial curve-based planners are more state of the art, like A-star planner, graph search plans, Dijkstra based, etc., or even probabilistic planners like RRT star. Motion planning, you get QP planners. I'm talking about velocity planning here, or backward forward method, or MPC. And for motion controls, typically PID, Stanley, Pure Pursuit, LQR. Also, these days more MPCs are getting used for controls as well, or iterative LQR, which is kind of a part of MPC, actually, a special case of MPC. The route planning is basically involves searching the navigation map for a navigation route plan from the point A to point B, or maybe dynamically from current location of the vehicle to the destination point B. For this, you have to basically create a road network graph where the nodes of the graph would be the junctions in the road, and the edges of the graph would be the roads itself. Then you can do graph search methods. Basically, there are a whole bunch of graph search methods, from your blind uninformed search like depth first or breadth first search, to more sophisticated search methods like A-star, Dijkstra, or even more complicated search methods like D-star light and all those things. So these are mostly well-researched topics, basically. Then I'm going to the path planner, which is the first part of the motion planning problem. A few different classifications of this problem I'm trying to mention here. One is geometric method. Then there are variational method, then the graph search method, then there are incremental probabilistic search methods. Again, like a lot of information given here, but I try to go a little bit high level here. That's why. So geometric methods are basically you have some parametric representation of the target lane. Basically, you have lane center and that you want to follow, and that using some kind of polynomial curve, and then you use another kind of polynomial curve to connect from your current location to that target location. Variational methods, direct collocation or indirect methods are more and more used today. It's basically more piecewise, functional approximation of your dynamic equations, basically. And you try to use polynomials to then connect those between those points, basically. There's a little bit kind of symmetry between geometric and variational methods in that sense. And variational methods can actually be imposed in both space and time domain, and they're pretty powerful. The graph search methods are basically you have your for the lot of different application of this. Mostly, I have seen like most of the use cases for constraint. On road, basically when you are driving on road, is usually geometric method or one of the graph search methods that are used. Variational methods or incremental probabilistic search methods are not being used. Usually they're done for more unconstrained spaces like parking lots and all. So graph search methods would be like, visibility graph, where you kind of divide your lane in, kind of uniform graph, spatial graph, basically, and then use Dijkstra, or motion primitives, which kind of I try to show here, where you're trying to, instead of like a spatial graph, you are trying to construct using some motion primitives, some more complex graphs, basically, in higher dimensional graphs, and then create a graphs, like you can see, you say like, I'll take 30-degree left turn or 60-degree left turn or straight. These are your motion primitives. And using that, you're searching the whole space, basically. And then on that, you do once you use that motion primitive, that's your graph, and then you use the graph search methods like Dijkstra. Probabilistic roadmap is another way of creating graph. Uh, it's a it's a little bit of probabilistic method in that sense. The graph is not graph is created probabilistically, basically, and you can use Dijkstra on top of that. RRG is basically the PRM is more um, so RRG, actually, let's go to RRT and then explain. RRT is rapidly exploring random trees. RRG is rapidly exploring random graph, basically. So trees and graphs are a little bit different in the sense trees start from one node and then it branches out. Like I kind of mentioned in this slide, this is your tree and this is your graph. Graphs will have this kind of might have this kind of cycles and all. The trees will not. Trees will each node will have only one parent, basically. So so for a RRT star, you start at RRT planets. Basically, you start at one start location, and you try to explore your search space using some random sample points. There are some logic. We're not going to details of that, and then kind of more like this kind of search space, basically. From each of these points, then you select another random points, and you kind of explore the whole search space like that. So this is more like a tree. So whereas the RRG is more like constructing a graph. So these kind of methods are, these are the graph search or your incremental search methods. They're all a little bit more computationally expensive. So they're usually need to be used for L4, L5 applications, whereas the geometric methods are usually what you see in L2, L3 space. The controllers, the whole bunch of different controllers. Once you get the sequence of, one thing I omitted is the velocity planning. Velocity planning is typically what, you get a path plan. Basically you get this kind of path plans, and then for each, in one path also you can have different acceleration profile and deceleration profiles to, or even jerk profiles to, uh, you know basically the velocity velocities, if you represent your velocity in time domain, then it can be different. So you can apply different methods, like I mentioned, even direct collocation methods are used velocity planning, but typically you can use polynomial curve, minimum jerk trajectories. Basically, given boundary value constraints, you can create a, again, like, I know that I'm throwing a lot of information, hard to not a little bit more time to know these things in more depth. So motion control is again where you have two different kind of algorithms, usually geometric test methods, which are what Pure Pursuit and Stanley do. Then you have more model-based dynamic model-based methods, basically, which would be like starting from PID, LQR, MPCs. They all do that. They use dynamic models, basically. So Pure Pursuit and Stanley